Good afternoon, everyone. Hi, I am Dr. Sakib Mahmood Khan, and I am the Assistant Director of the Center for Connected Multimodal Mobility, or C2M2, which is a sponsor of today's webinar. And I am also as working as a research assistant professor at the Civil Engineering Department at Clemson. And today I am very pleased and I am very honored to introduce our distinguished speaker for today's talk, Dr. Bing Lee. So, a short bio about Dr. Lee is Dr. Bing Lee is an assistant professor and director of the Auto AI Research Group in the Department of Automotive Engineering at the Clemson University International Center for Automotive Research, or CUICAR. Dr. Lee received his PhD in electrical engineering at the City College of New York of the City University of New York in 2018. His current research interests include computer vision, AI, sensing and imaging analysis, assistive technology, autonomous robots, and vehicles. Dr. Lee is a pioneer in computer vision and AI as sensory substitutions for the visual impairment assistive navigation. Dr. Lee is recognized with multiple national and international best paper awards, and his research has been reported in top-tier computer vision and robotics publications. So today's talk will be followed by a question and answer session. So if you have any question for the presenter, Dr. Lee, please feel free to type it in the chat box at any time, and I will read it in the question and answer session. Or you can raise your hand and unmute yourself in the question and answer session after the presentation ends. So at this time, I would like to turn it over to our distinguished guest speaker, Dr. Bing Lee. So Dr. Lee, we're really excited to hear from you about your exciting work.
Okay, thank you, Dr. Kahan. Good afternoon, everyone. I'm very happy to be here today to introduce my research on the computer vision and AI-based assistive navigation for the visually impaired and blind travelers. This research is sponsored by USDOT and also the C2M2 Center. So before we start, maybe I think all of us, we can thinking about, or maybe you have some of the situation, maybe your family member, or maybe your classmates, or maybe your neighbors. So they have some of the situation when they are trying to, like in terms of the travelings, either indoor or maybe outdoor, for the study or maybe for the daily activities, like all of these commute independent travelings. So, and today's topic is more introduce some of the research me and also my group has been working on in the past few years, and also right now. We are trying to working on the computer vision and also the AI techniques to empower the sensing for the visually impaired individuals. And so for the top left picture is showing a scenario in the indoor environment. And so some of the, we don't know, I mean, we have, as a normal sighted person, we naturally, we understand the environment. We are able to remember where we have been to any of the environment. We have this kind of memory is able to help us to navigate. And when I was doing the research, I did some of the tests. It's called blindfolded. It's like your blindfolded your eyes, and then you try to navigate in the environment. And I did a lot of these kind of tests. And then it's not only one time, I would say it's more than 50 times. And it turns out, actually, it is a very challenging work. Even we, as a sighted person, we have all of the skills we learn to navigate in such an environment. But actually, it turns like when you blindfold yourself, you're gonna lose the orientation. You're gonna lose your where you are, for example. So certainly, there's some of the challenges over here is how we can thinking about some solution to help the visually impaired individuals to, for example, how to help them to navigate and how to help them to be aware of the surroundings. And another situation certainly is like in the outdoor, especially in the transportation chain. So there are even much more concerns in terms of like understanding the traffic environment, right? And also the even like the traffic light, or maybe some of the vehicles which is coming towards the user. So even there's some new challenges. For example, the electric vehicle, actually, so they have a relatively, so compared with the combustion engine vehicle, so it has a very low volume noise. So yeah, whether the blind individuals, they are able to be aware of the situation of the electrical vehicle which is coming maybe nearby. So certainly one of the very essential in the mobility or in terms of the wayfinding is from A to B. And in the era of the autonomous driving and all of the vehicles and also the public transit, so one of the research gap me and also my group has been looking at is how to bridge the first mile and the last mile assistive mobility, assistive navigation for the visually impaired. We hope to, through the AI and also the sensing technology, so we are able to help the visually impaired, help them to navigate inside of the building, help them to navigate from the building to the public transit near the home, for example. Of course, another side is the last mile, how to help them to navigate from the public transit to inside of the building. So the number of the statistic in terms of the blind individuals, the numbers are increasing. I remember first when I was doing some research, beginning I was using some of the data in 2014 and then 2017, and then WHO has 2020 data statistic showing the number of the individuals who has a visual impairment. And also in US, there are more than 12 million individuals has a certain level of the visual impairment. And also some of the diseases, and also for the elderly individuals. So all of these, the reduced or absence of the eyesight certainly has a significant impact for the daily life. all of the opportunities. And as we can imagine, we had some of the user study, for example, with visually impaired. So, okay, so sometimes it's pretty easy for us to thinking about what kind of concerns over there. But when we are conducting the research, the user study, so it really happens. I mean, so for example, we had the user study with a local group in Greenville. So the subjects tell us some of the concerns. For example, so she has to go to the grocery shopping, for example, every week. So she lives alone, and every time actually she has a lot of the trouble. For example, to get Uber or Lyft, for example, and how to approach the vehicle, for example, and how to get into the store and then do the shopping, and then how to get another Uber or Lyft. Of course, certainly work opportunities. So how they can be part of the community or some of the job opportunities. So all of these come back to the essential needs is independent traveling. So in our study, a lot of the visually impaired subjects, so they really rely on the family members. But certainly there are some of the subjects, so for some reason, so the family member cannot be support their daily activities. So how they can have the independent traveling? We know typically we have the blind individuals. They rely on the guide can, the white can, and also the guide dog. However, all of these, they are still has a limitation, is like they're only able to handle some of the situation. So for example, for the guide dog, so it is trained to help the visually impaired. For example, it try to follow a certain sidewalk, but it is not trained to bring the individuals back to a certain location. So how we can use the technology to, of course, I mean, the technology can still work with all of these tools to finally to support the independent traveling. That is the research focus in this study. So in the area of the deep learning AI and also computer vision, so how about the visual sensory substitution? We know the deep learning, the high performance computing, edge, cloud computing, all of these bring the opportunity to have the infrastructure or the computing and intelligence models to support such kind of visual recognition. So we take this picture as an example. So we can think about what the AI will need to do to assist if we are blindfolded, or for the visually impaired, or for the blind. So probably the AI should recognize the sidewalk, right? should recognize the street and maybe recognize some of the fence, for example, right? Maybe some of the like bushes, trees, for example. And also maybe the AI should help to understanding whatever, for example, all of this information in case which is as a destination for the visually impaired. In addition to that, so actually there are a lot of other concerns, right? So the AI also should recognize the traffic situations, recognize a vehicle, for example, or recognize any other traffic agent inside over here. And nowadays, this is showing a typical AI segmentation model. So in terms of the visual recognition, segmentation model is a typical model is try to segment different kind of objects or maybe different kind of object instance for the whole scene. And if you see over here, basically categorize what kind of scene category it belongs to. So for example, here's a sky, and then here's a sidewalk, and this is some of the buildings. And all of this technology actually has been used in the autonomous driving. So for example, this is the what in the Tesla autopilot eyes, the street view. So it is try to understand all of the moving objects, and also is try to identify or maybe segment the traversable areas, the drivable areas. So in terms of for the visually impaired, so one of the main thing in our research is what is like the computer vision need to understand, and whether the AI is able to resolve any of the concerns, any challenges for this research gap. And what is the drawbacks, what is the limitation, and what is the user concerns? That is some of the aspect during our research we have been investigated. And as a final, maybe a solution, or maybe like in our user study. So certainly nowadays, everyone, also the visually impaired. So everybody really count on the mobile device, for example, instead of like to have another carry another heavyweight assistive device. So the visually impaired is also preferred to have the portable mobile device is able to basically as an assistive device for the assistive navigation. So in our research, we call a safe and efficient wayfinding, C-way. And the main challenges in such a research gap is if we're thinking about the problem from such a intuitive way, so we need to know where we are, right? So this is showing an example like how to use the sensors, typically in this case, it's a 3D LiDAR, to travel inside of the building, and also travel from the indoor to the outdoor, and also from the outdoor to the indoor. So the first concern is where am I? Especially in the considering our scenario is like to help with the first and last mile scenario. So if it's near the building or inside of the building, the GPS is not reliable. Basically, there's some of the multipath reflection concerns. So even your device is able to get the GPS signal, so it's not accurate enough in terms of where you are, right? So probably it's going to be 10, 20 meters away accuracy. And some other concerns is like what? So what kind of information need to be identified, especially for the assistive navigation for the visually impaired, and also how. So how to compute for that. So naturally, we have a good idea in terms of traveling. We have a good sense in terms of like from a certain location to another location. However, so how to represent the environment and also how to find the path for the wayfinding. So that is another challenge. So this is three fundamental challenges. And in addition, so the dynamic concerns. If it's an indoor environment, so the dynamic object, maybe the people in the surroundings, or maybe other safety concerns. For example, if there's some of the object, and also even some of the situation, maybe stairs, for example. Some of these dynamic object, some of the object which has a safety concerns for the user. And it turns even more challenging in the first and the last mile when in the outdoor environment, especially detect any potential vehicles, for example, and also understand the traffic situations. So this is the outline for our research talk today. First, I'm gonna introduce what we have been working on for the computer vision based navigation. So start from the overview, and also I'm going to introduce how we use the vision to do the positioning, and how we use the vision to do the map, to build the maps, and also how to build the Simatic maps, and how to use a visual recognition to detect the object, and also to do the obstacle avoidance. And then I'm going to introduce another recent research we have been working on, is using another approach to combining with the language into the human in the loop. In that case, is an approach which is different with what in the beginning over here. So I'm going to introduce how we can build and model the scene as a graph. And I can introduce about the visual language navigation AI model training and evaluation. This picture just shown a concept of like, we would like to have such a portable solution with visual perception, and also with human machine interface, which is able to finally serve for the blind individuals. So for the computer vision based navigation, so if you look back into the robotics technologies, some of the research has been working on like design the electric cam. So for example, this is a research has been done for the smart can. So basically, some of the sensor has been installed on the can, and and also have some of the, even for the CAN, for example, there's a running model is installed, is try to provide the active guidance. In this case, probably is like for the direction, right? And there are also some of the research. Here's an example to design the robotics guide dog. So have the robotics is able to do the robotics navigation finally to assist the blind individuals. And in the past few years, Google Waymo has been a pioneer to basically to provide the a solution using the autonomous vehicle to assist the blind individuals in the transportation chain. And in COICO, we also have been basically, we try to leverage on the OpenCAV autonomous vehicle to assist to bridge the transportation gap to try to have the visually impaired blind individuals is able to use the research in this talk and try to access the vehicle. So the robotics design is a good reference for us to thinking about how to design a solution and what kind of concerns when we try to design a solution for the visually impaired human subject. So the main design philosophy in our research is we have a human-centric design, human-centric AI, human-centric decision making. For example, for the robotic dog, basically is like it's more like a robotic solution rather than assistive solution. So for our design, we try to have the blind individuals to gather the information from the sensors, from the computing platforms, and then to make the navigation decision. And we have been working on different kind of platforms. So for example, we have been working on the like a computer or like a Linux solution. We have been working on like the mobile tablet. We have been working on like a mobile cell phone solutions. So basically, I've been looking into a cloud and also edge co-design solution for the human-centered design, and use a computer vision to as an artificial eye as a visual substitution for the user. And for the navigation guidance, so robotics, so they have a way like computing path planning or like switch the path. So so my group has been investigate some of the, for example, the user started to identify what is the needs and what is the concerns in terms of the user human navigation, right? So typically, like we as a human being, we naturally we're gonna rely on something like a certain waypoint, or maybe like in which location we're gonna make a left turn, we're gonna make a right turn, right? And also surrounding understanding. So the kind of AI, so we see that a lot of the model is able to do detection or segmentation. But what it really matters in such a, in terms of to bring the situation awareness for the blind individuals. So this design basically we have been focusing on such indoor or outdoor transition scenarios where GPS is not reliable. Yeah, this is showing some of the sensors and also the HMI devices interface. We have been looking at like the cameras and also the camera glass, and also positioning sensors like the initial measurement unit. And for the interface, like vibration, like a visual display, and like audio, and also the voice interaction, for example. So let's take a look at the positioning. So from the robotics navigation perspective, so the main concern started from like, where am I? Typically, we use the we call it something like called a pose, like including the transition and the rotation of a certain the user, or maybe like the sensor, right? So the translation is normally like X, Y, Z in the 3D space. Of course, it can be also simplified into the 2D case. If we're considering the environment is only like for the as a 2D plane transition. In the rotation, basically is like in the 3D case is gonna be like including the orientation angles, or maybe in another representation like the quaternion representation. And for the math completeness, so it is normally represented by the translation, which is the 3x1, and the rotation. And in terms of the navigation, the path planning, the mapping, everything started from the coordinate systems. So normally we're going to have the world coordinate, and then for the user and also for the sensors, and especially for example, so where am I in terms of like with regarding to what? So it is should be with regarding to the map, right? So that is the map. We need to build the map, and then to be able to be aware of like all of the information in the environment in the world coordinate. So in this context, so the problem would be is trying to identify the transformation between the user or the sensor to the map. Yeah, so this case in the user and the sensor, they could also have another, I mean, they also have a different kind of coordinate, right? So of course, you can choose the coordinate system of the user as the coordinate of the sensor. That's also very normal for the assistive navigation. But for the robotics navigation, normally that's separate. So we have been looking into the visual positioning and also visual odometry approach. From the front end perspective, so it includes first start from the feature detection and the feature matching, feature association, and then the visual odometry calculation and the multi-sensor fusion to basically to fuse the odometry information. And so we have been looking to we have been explored multiple types of the visual odometry solutions, like the LiDAR solution and also the LiDAR IMU solution, visual and visual IMU solution. And in this research, we have been working on the visual and initial, which is a very typical combination of the sensor in a lot of the which is on board for a lot of the sensors, for example, and also it is a very it is equipped on all of the mobile device. We have been working on some of the feature detection based on the geometric approach. So, for example, some of the gradient-based features. So, for example, the shift, the surf, for example, and also we have been looking into some of the learning-based approach, like ORB or some of the deep learning-based approach, to extract the feature and then to perform the feature association. And on the backend and optimization side, we have been applying some of the nonlinear optimization approach within some of the existing solution like the GTO. We built we call something called the core visibility graph for the visual positioning keyframes, and then finally the lobe closing and the boundary adjustment is applied to optimize the location estimation of the camera, of the visual odometry and positioning. So this is showing some of the result of how to perform the localization and then to project the observation of the environment into the same coordinate. And this one is showing the a comparison result of our visual odometry and with the ground truth, and with some of them with only the visual odometry and with the lobe closure, the accuracy. So this is in the office environment. So the size, basically the ground truth was chosen basically to work like in the middle of the hallway. As we can see, for example, the visual odometry approach, it has a certain level of the shape, like drift, right? For example, especially in this kind of place. And the one with the lobe closure, so basically it is much more close to the ground truth, and with such a level of the accuracy. So in such a scale, like 30 meter by 50 meters, such a floor, such a office floor. So the accuracy is pretty decent to support, to enable the path planning to do the navigation. And based on the positioning, so in terms of the mapping, so we have been working on different kind of perspective for the maps. So the first one I would say is like a feature map. So the feature map is corresponding to what we mentioned over here, the keyframe. So for any of the keyframe, we're gonna record all of the features. So for example, all of these features over here, and in terms of the continuous frame, how to compute a continuous frame and then how to fuse a continuous frame. So we have been looking into some of the it's called a computer vision association, and also 3D registration problems. So basically, to model the problem of the continuous frame registration as an optimization problem, essentially is trying to find the 3D the transformation in the 3D space between the continuous frames, and to formulate such optimization cost function, and we have been working on some of these registration algorithm, like the RCP, to basically to optimize and then to calculate the to estimate the R and the T. In addition to the feature map, we have been also working on basically is to fuse the map as a dense map from 2 frames and then to multiple frames. So of course, this is like the map for that flow, office flow. This is showing an example. Basically, we after we create the 3D model for that flow, and then we try to simplify. Basically, we try to get the 2D map, get the 2D projection view for that flow, which is used for the path planning. In addition to the geometric mapping, we also have been working on the Simatic mapping. So the Simatic mapping is based on the geometric positioning and the geometric mapping. And then we have another channel is able to have the input from the RGB and the depth channel. And we have been designing some of the network to recognize and also segment the different kind of object category of the environment, and finally to represent the result in the 3D model with the visualization recognition category. So what we have been doing, basically we have been started from, we was using a unique structure of the segmentation model. And then we designed an edge detector to basically to concatenate some of the features from the encoded level and then with decoded level. And as a result, so basically such a network design is more sensitive, is able to capture more for the edge conditions. And also it is better to recognize the small objects. And in addition, we have the option is like we are able to use a depth channel information to fuse into the network to improve the segmentation accuracy. For the model, we have been using the NIU RGBD dataset. Basically, this is like dataset including 1,000 this number of the images and with such a level of the object instance. This is a number of the class. So this is a very typical indoor segmentation of the dataset. And this is showing the RU accuracy during the training and also the max F1 score. And this is showing the basically the training the loss in terms of the iteration. This is showing the result of our model, the accuracy in terms of the pixel average for all of this category. This is for the RGB and for the RGB and RGBD. Another concern is to have how to fuse continuous frames in the temporal domain. For example, in the first frame, so it is going to have a prediction result. And in another next frame, how to fuse them, we have been using some of the approach called a conditional random field, which is an approach based on the probabilistic Bayes fusion framework, basically to have because any of these prediction, it comes with the brief brief in terms of each category. So we are able to use such a probability propagation to update the belief of each category in the continuous frames in the 3D model. This is showing the result. Here is a pure RGB image, and this is the golden truth in the data set. This is showing the result of the, before we're doing the conditional random field, if we use a pure registration. So it's going to be relatively, it's more noisy. And then after the fusion of the continuous frames, so it becomes more, especially for some of the objects, for example, they are able to improve the observation estimation belief. And here shows basically in all of this category. And this is the first over here is showing the result of the RGB, and this is the RGB and then plus the fusion, and this is the RGBD and RGBD plus the fusion of the continuous frames. Now this is showing the result of the basically the semantic segmentation and mapping for the 3D model. So everything over here is in the 3D model. It's not in the 2D image. And as a last step of the map is to basically to align the computer vision map with normally we're going to have a GUI map. So basically we'll be using some of the semantic alignment approach basically to align such a map with visualization as a GUI to the user with whatever the positioning keyframe map. So this part basically is like recognizing some of the, in all cases, basically we try to recognize some of the, for example, some of the landmarks, and then to use a landmark to as a control point to formulate the optimization. Finally, to basically to resolve such an optimization problem using such approach such as the SVD. And based on such a map, we were building the navigation graph, and then for the assistive navigation purpose, basically we are trying to first we still have the path search, and then for example some of the search algorithm or maybe a star or digesture or some other algorithms, and then we design some of the approach called path pruning. We are trying to basically to simplify the path when the user is doing basically this part is doing online. So when the user is moving, is walking, so we simplify the path. For example, when the user come over here, we're going to simplify the path from here to the next waypoint. So finally, the path and also the navigation guidance was go through voice and audio interface to guide the user. Another concern is the obstacle detection and avoidance. So we have been exploring some of the 3D detection and the 3D basically based on the 3D point cloud data, and then to by for example by detection of flow and detect all of the walls, and then to detect any of the off-ground objects which is in front of the user. And then this is showing a visualization of such an object in different kind of projection. because we were trying to, because our map was simplified for the 2D, so the 3D detection was simplified into two 2D direction. So one is like a the top view projection. Another one is a front view projection. And we tried to build such a, we call it VFH cost. And based on this cost, and then we tried to, of course, the projection was updated into the map, and then we designed some of the strategies. We're able to basically to, based on the obstacle, we're able to update the path from the current position to the next waypoint on the fly. This is showing a system evaluation for the first prototype. It was done on the ROS robot computing operating system on the computer. So this is showing the mapping. This is showing the positioning on the map. This is showing the final test in terms of the interaction with the user to navigate from this location to this location. And then we did the design on the prototype on the mobile device. And we have the blindfolded subject and the blind subject experiment. Basically is able to, through the audio interface, we're able to guide a user to from A to B. And in addition, we have some other research has been working on is to recognize some of these potential hazards in the path, or for the like a stairs detection for the safety concerns. So what I've introduced basically is a computer vision approach, but it is a robotics way. It is a robotics way to do the navigation and then to positioning the system, positioning the user, and then have the maps, have the path planning, and motivated by the human navigation. So when we are navigating in the environment, we just rely on the visual recognition. We rely on some of the end-to-end design and like from A to B, and also we rely on some of the language or some of the, for example, we can get some of the path description by asking some of the people, right? So, and then we are thinking about how we can design a more intuitive way for the human users. And we was coming up a solution using the visual language navigation model to do that. So of course, we're gonna still have the visual positioning, visual localization, all of this part. However, the navigation actually is not rely on this part, but no matter what, I mean, this is like as a baseline, because you certainly any of the navigation, especially as a guidance to the user, so you need this part. So we assume, so the system is able to get instruction from, for example, from a certain place, from a certain through another device, or through just from the language, like a description. And then we build such a graph map. And then finally, basically, the model is able to predict such a path for the user. So in this context, we design such a VLN solution. So first is like we have been using some of these simulation environment to train the agent, and we by collecting some of the the data. It basically is a skybox 6 images for each location. And by training such an agent in a simulation environment, we generate the scene graph based on some of these ray tracing algorithms. And then we design our VLM model based on some of the visual language models called ENV drop. And we train such a model in the Matterport 3D dataset. And we also collect and also create our own dataset. Finally, it is deployed on a cloud and edge solution, and with a path generation and visualization, and also with the online obstacle avoidance. So this is showing the dataset and the training. So this is what we use for the training. This is the dataset we create in Clemson library. One of the dataset we created. And this is a typical, we categorize the instruction into different kind of category. So the first one is only direction. So basically the direction is only describe which direction, but this one basically is going to give you some of the context in terms of what kind of object inside of the environment. And this is basically to combine both. And we did the evaluation and evaluation study, and it shows that basically the heuristic-based instruction basically performs better than the other ways generally. And the reason is like the VM model is able to leverage on the path search, and then by combining with features and objects by the recognition. Another evaluation study we did is the success rate in terms of the navigation path. So when your path is much far, so basically it's going to have a higher failure, has a prediction failure cases. So it's such, so this result suggests a certain distance for us to re-incur in the path during the navigation within such kind of model. This is showing the result basically in our own data set. This is, in this case, basically the both align on the ground truth and the model projection aligns. This is showing a start path. This is slightly different. This is in the engineering building. So this is in the library. So this is showing in the Matterport 3D dataset. As you can see, the model is able to perform relatively reasonable, and in terms of the all of this, basically all of this, and also this one is an on-sea data, is an on-sea environment basically. In addition to this, we also has been basically to handle the local the obstacle avoidance. Basically, the graph is going to be like all of these red is, and if there any object which is overlaid with a graph path, and then we have been working on like the ground detection, ground segmentation using some of these computer vision algorithms. So we're able to detect, for example, the chair is overlaid with the path, and then to perform such a local replating for the obstacle avoidance. Yeah, so that concludes my presentation. And so this basically introduced some of my research activities and some of the research. If there are any research alignment, looking forward to collaborate with you. Thank you.
Hi, please write your question in the chat box, or you can speak up.
Hi, Dr. Lee. Thank you for your presentation. So I had a question about the deep learning model that you showed for the when you fuse the RGB image with the depth image.
Yeah.
So what fusion technique do you use to fuse the images before feeding it to the deep learning model?
Okay, actually there. So first, so the sensor, the calibration, and we did the sensor calibration basically is to make sure the RGB channel and the depth channel is able to align, and also for the depth, we are able to basically to estimate the depth uncertainty. And then in terms of the fusion, basically it is done in the network. It is not done before the network. So the network is going to input the RGB channel and also the depth channel.
Okay, thank you.
Yeah.
So there is a question in the chat box from Mahfuz, and
Yeah.
what he has 3 questions. So first one is, from the product point of view, as to run a deep learning model, we need a computing device, ideally a GPU, by the person or for the person, how it can be done. That's the first question.
Okay, so that is a good question. So when in some of the early research, basically we was using some of the computer which is not with much AI capability. I would say so there are much more and more AI computing capabilities in the edge device, so which allow you to deploy some of the AI models. And so certainly for the mobile, for example, the mobile net, which is a typical model, which is lightweight, we're able to deploy to do the segmentation, for example. However, certainly there's the bottleneck in terms of the model accuracy, the trade-off. So in that case, so basically we have been working on some of the AWS solution to bridge both in the cloud and in the edge side. So for example, for the visual language model, actually it is done in the server. It is done in the cloud. Yeah, but you don't need to inquire the path in any frame, right? So you just need to maybe occasionally you're gonna just submit such a request to get the path.
Okay.
Yeah, that is for the second question. For the inference of the deep learning model, so the AWS, for example, they have a pretty good such it's called a request. So it's not well support for the streaming. So if you wanted to stream it for the AI, streaming your sensor data to the AI server, so that is much more challenging. But if you're doing the query, the processing request, so that is can be very easy to done in such a infrastructure.
And third question, if the system runs locally, the SLAM segmentation and avoidance is running on the computing device at the same time. Can the system produce a real-time output for the impaired person?
Okay, so so in this case, for example, the segmentation I've been showing that one is a more heavy computing way. So that one is done in the server, but we have been working on some other lightweight. But in that case, basically, yeah, still, I would say the segmentation is normally much more computational heavy. So maybe, yeah, basically in our research, we also have been working on some of the detection model. The detection model, which is relatively, that's more lightweight for the, especially for this kind of edge computing. So from my research experience on this kind of real-time system design. So there are a lot of the conventional computer vision, for example, for the ground flow detection, for the object detection, for example. So even we have been working on some of these AI-based detection. So still, when we deploy the solution, we are more working on some of the more conventional geometric-based computer vision algorithm, because it is much more efficient to detect object, and then to be able to have a strategy is able to do the local obstacle avoidance.
So Mahfouz expresses thank.
Yeah. So Dr. Lee, I have a question. So you said the geometric based AI. So what did you say? I didn't get the last phrase.
Okay. So basically it's like, for the real-time system, so basically the trade-off in this kind of real-time system is like real-time performance,
right?
Real-time characterization, and the sensing capability, right? So I would say, of course, I mean, the mobile device or all of these edge computing on the autonomous vehicle, they're much more and more powerful AI computing capabilities.
Right.
However, in our design, my experience is like still, it's more like a combination of both to do the navigation job.
So what are the both? So what are the two things in both?
So for example, the geometric solution, it can be like build the slam maps, and also to do the odometry. Basically, is relatively lightweight.
Okay.
And then for the AI, so it is doing some other work. For example, so a typical example, if we try to recognize where we are, we are trying to inquiry from the memory where we are. Right? So there's some of the AI model is able to help with such kind of it's called localization. So but this part is able to do in the backend. It is able to be done by a request. So in that case, basically, so basically it is in the on the edge side, it is done in the backend solution.
Right.
So there's some of the backend thread is doing that job. So it's not gonna affect any of the real-time high priority tasks.
Right.
Yeah. So for all of the AI model, for example, some of the lightweight detection, so it's not necessary to be done in every frame. So that is something like in the conventional geometric computer vision. So it has a keyframe. So identify the keyframe. So you only need to do some of the detection recognition in the keyframe.
Okay.
Yeah.
So I just have one comment. So yeah, you mentioned about AWS or any cloud computers, but then you have to look very carefully if it is, especially if it is commercial computing, because how long it will take, right? Sometimes it could be queued. So yeah, so if you're using any commercial cloud, then you have to look at different issues related to commercial cloud computing.
Yes. So so we have been looking into some of our own server, and also we also have been looking into the basically it's like I would say the commercial or some of the solution, it become much and more powerful than we expected. It's like more than what I thought. Like some of my experience maybe it's a few years ago. And
so what is more powerful, Dr. Lee? So
for example, in terms of like the storage, the streaming, and also the computing, the infrastructure. So it is basically it's like it is very powerful, and also of course, I mean, it looks like, I mean, they have some of the trial solution. Basically, it's like in the research, we don't need to pay for that. Yeah.
You're talking about cloud, a commercial cloud, right?
Yeah. So that is something like we have been exploring both on the own server. Basically, it's not necessary to be like a commercial, but it's like we are more exploring how to distribute the computing AI computing in both cloud and edge setting. What kind of like work should be done in the back end, and what kind of work can be done in the front end? That is a generic concern.
Right. So we have one. I think it will be the last question because we are already over time. So Sabir is referring to slide number 18.
Yeah.
If you look in the chat, the two cases you showed are GBSF CFR. What are the difference between those two cases?
This one, right?
Yes. Yeah.
So basically, the RGBD basically is only with the registration. So you don't fuse the temporal frames. However, from the research perspective, I mean, it really depends on how we design comparison experiment, right? So in terms of the peer registration, and in that case, basically it's like you just update based on the new observation. And the CRF basically is more like each of the frame, basically you have the prediction, you have the accuracy, you have the belief of your observation. And then all of this belief is going to be updated through the Bayes framework, Bayes methodology. And then so you're able to fuse the continuous observation, the result.
And it updates it, right?
Yes. Yeah. So it's like a Bayes updating Bayes belief propagation. So you can get a more stable, less noise observation.
So Sabir, do you have a follow-up question, or you are okay?
No, Dr. Shruti, thank you. Yeah, I'm good. Thank you, Dr. Lee.
Okay.
So thank you so much, Dr. Lee. It was wonderful. So thank you so much for being our distinguished speaker today. We learned a lot. So thank you.
Okay. Thank you, everyone.
Thank you.
Thank you.